recording now. And basically, what we're going to be doing today is we're going to extend the concept of a limit to one of the major calculus operations that we're going to learn in MAT213, and that's something called the derivative. You might remember we've been talking for the last week or so about average rate of change, which you can represent on a graph by drawing two dots that are pretty far apart on the graph, drawing a line through those two dots called the secant line, and finding the slope of that line. That's an average rate of change between those 2 points. If you want to find the derivative, what you're asking for is an instantaneous rate of change at a particular point on the graph, okay? And what we've done so far is we've approximated this, okay? And we're going to do a little approximating again today. And then what we're going to do is we're going to use the idea of a limit to essentially take the slope of a line between 2 points, but we're going to make the 2 points be as close as you want them to be, as long as they're not the same point. That's where the limit part is going to come in. How close? Well, let the distance on the x-axis between the 2 points approach 0. How small do you want it to be? Okay, so that's kind of what we're doing. Please understand, we're still finding a slope. Okay, so a derivative is a slope. Okay, it's just using the concept of a limit in order to get there. Okay, so I'm going to start sharing my screen with you. Okay, I'll start out with my browser. Right, and I'm going to hopefully show you our Canvas class. I just want to show you where we're at. We're in week 3. Okay, and you'll notice there's only one topic in week 3. That's because we didn't have a session on Labor Day. So this is the one section we're going to do. There's only one homework assignment on the derivative, and there's a grade check. Okay, I want to show you a grade check is pretty much a way for you and I to talk in this weird environment we have where we're not seeing each other in class. And it's, again, a way for you to look in Canvas, all right, and determine what your grade is, okay? I'm going to ask you in the grade check, what do you think your grade in the class is? What assignments are you missing? Okay, and do you need help with anything? Okay, so you click on your grades, like if you go up here, again, I'm going to get something different, okay, and I don't want to compromise anyone's privacy by clicking on this. But for example, if you were to click on grades, it will list all your grades, and all the way at the bottom is your overall grade in the class, okay? Now, please realize anything that's gone past due has probably changed to a 0, all right? And if you want to work on those, you've got 3 days to use a late pass, okay, to open up a more assignment. If it's an assignment in Canvas, such as a discussion board or a survey, right, then those things you can work on even though they're past their due date. There's no late pass required. The only ones you require a late pass for are the homeworks. Okay, so again, hopefully that's clear to everybody. If it's not, please reach out, either that or you can type a question in the chat, because I have the chat open and I will keep looking at it while we move along. Okay, so again, to scroll on down here, in week 3, all right, here's where I'm going to put the video, and any notes that I share with you, anything I write on will go here. Okay, you've got your videos and textbook here, and again, these are the materials I'm going to be using. Okay, so I'll be writing on definition of the derivative exercises in case you want to print those out beforehand. Okay, anything I'm going to be using to write on, okay, will be in supplementary materials. And again, I'll upload whatever I create in here along with the video link, right? So you'll have everything that I work on. It's just if you want it in advance. Okay? Also, I want to draw your attention to this. Whenever I come across an applet that's really, really useful, I'll put a link to it in here. I have this applet open, and we're going to be using it from time to time while we go through the derivative material today. Okay. Again, apps are fantastic because calculus is the math of things in motion. So why not use an app to put stuff in motion? Okay. It's a lot better than trying to draw 50 million drawings to illustrate what happens as I move around this graph. Okay. So you have a link to it. And again, I'm just showing you where everything is here. Okay. So anybody questions before we get moving? Any questions? Okay. So I'm going to start with, again, the derivative textbook. This is kind of what I'm opening here. Okay. And I'm going to use that as a guide. So let me share my content with you. All right, so you should be seeing what essentially looks like the textbook, right? And basically, what I've got here is a description, a definition of a derivative, okay? So again, we have part of a graph, okay, and you can see it looks like a quadratic, the red line, okay? And what we've got is a blue tangent line. Remember, tangents touch the graph at one point. Secants actually go through the graph at 2 points, okay? And if you push the 2 points closer and closer together, okay, you pretty much change that secant line into a tangent line. It moves from being inside the curve to outside the curve, touching it at one point. Now, what you could do if you wanted to estimate the slope of this blue line, because again, our derivative is the slope of a tangent line as it moves around the graph. And you can see that slope would change as we moved around the graph, okay? Here, this blue line has a pretty steep positive slope. But if I were down here, I'd still have a positive slope, but it wouldn't be as large a number. And right here at the bottom, at the vertex, okay, the tangent line would be horizontal and it would have a 0 slope. So you could see, unlike a linear equation where the slope of it stays the same, as I move around the curve, this tangent line slope is going to change. Okay, and that's the thing we're going to track with this function called the derivative. Okay, so what they're showing you here is you can start out. Okay, you see the black secant line here? It's between the points 2, 4, and 3, 9. Okay, and it's meant to be an approximation to this tangent line. And you can see here, it's not a terribly good approximation, right? The secant line has a bigger slope. Okay, how can you get a better approximation? Well, see what they're doing in the second graph? They're pushing this point down from 3, 9 to 2.5 and 6.25. They're making the 2 points here closer together. And now the secant line slope is close to the tangent line slope, closer. Okay, still not great, but closer. All right, and they actually do some calculation over here, right? They're saying if you use these 2 points over here, 2, 4, and 3, 9, okay, you can calculate the slope using your friend the slope formula, okay, which you might not have seen as delta y over delta x. You might have seen it as y2 minus y1 over x2 minus x1. Delta, again, is a Greek letter, and it means change, okay? So if you take the difference between your y values, right, over here, 9 minus 4 on top, 3 minus 2 on the bottom, you're going to get 5 over 1, or a slope of 5. And again, we could see this had a pretty steep slope, the black line, okay? And like they say, it's an estimate, and it's not so good, because you can see these 2 lines obviously have a different slope. So here's where they're picking a slightly closer point to 2, 4, okay? Notice you can't move the 2, 4, okay? That point staying the same, okay? And they're picking this point, 2.5 and 6.25, okay? And they're trying to get a better estimate of the slope. Now you can see, hopefully by looking at this graph, the slope of the blue line is positive, but it's a smaller positive number than the slope of the black line. The black line's steeper, right? So that slope value should be a bigger number. So if we want a better approximation, Okay, and remember the slope here was 5. See it up here? We're expecting a smaller positive number as the estimate. Okay, so if we plug in these values, okay, where say y2 is 6 1/4, okay, y1 is 4, x2 is 2 1/2, and x1 is 2, we get this slope down here, and we get 4 1/2. A better estimate, but still an approximation. Okay, so rather than think of the 2 points moving towards each other, it would be better for you to think of the secant line slope as an approximation to the tangent line slope. Okay, and I'm putting that in the chat. Okay, so the secant line slope is an approximation to the tangent line slope. Does that make sense to everybody? Make sense? Okay, as we're moving along? Okay, good. So what they've done down here is they're saying, well, let's look at this graph and let's pick a bunch of points that on the x-axis are to the left of 2, 4, and then let's pick a bunch of points that are to the right of 2, 4, and let's use them to calculate the slope of a secant line between whatever that point is and 2, 4. So here's what they got. They got this table. Here are the points to the left. Notice all these x values are less than 2, okay? Some of them are very, very insignificantly less than 2, right? And here are the y values that go with those x's. How'd they get them? They squared the x, right? Because we started out with a function y equals x squared, okay? Then they're calculating the slope of a line through x, y, and 2, 4. How are they doing that? Well, this is going to be x2, y2, and then 2, 4 will be x1, y1. Okay? And you can see as x gets closer and closer to 2, what's your slope value getting closer and closer to in this left-hand table? You can see it's getting closer and closer to 4. Okay, and again, that's the slope of a secant line between 2 points. They're doing the same thing to the right of x equals 2. They're starting out as, okay, let's start at 3 and let's back up towards 2. Okay, so they go 3, 2 1/2, 2.01. This is very, very slightly to the right of 2, yeah? And then they got the y values the same way by squaring these. And then they found the slope between the points they created, x and y, and 2, 4. And you could see here the slopes are going down. Okay, they're going down again, approaching what value? And what are these slopes approaching for? Okay, so these two tables are telling you approximately what the instantaneous rate of change of y equals x squared is at the point 2, 4. Okay, they're telling you the slope of that tangent line must be 4, because as I get closer and closer to it, okay, you can see the slopes are approaching 4 from either side. Okay, everybody all right with that? So again, the only thing that's special about the x values is that we picked them to be very close to 2. See them right here? This is 1/100th away from 2 on the left, and this is 1/100th away from 2 on the right. Okay? In order for this to make sense, you're going to have to go back to your understanding of numbers and realize, well, how close is this to a given number? Okay? And again, you can realize if I put another 0 in here, I'd be even closer, 2.001, right? Just like if I added another 9 here, I'd be even closer, 1.999. That's 1/1000th away from 2, yeah? Okay, now eventually you hit the limit of your calculator, okay, which is a problem on a TI-84. not so much on a modern app, okay? But just realize if it tells you, oh, the answer is exactly 4, it's not, okay? Because again, then you've hit a rounding situation, okay? So let's take a look, okay? That's the point, that's an estimation of the slope of a tangent line at 2, 4 here. So what we can say is the y values are changing at the rate of 4 for every 1 that we move over to the right, okay? Which would be great if this function was tracking something like profit. Hey, I sell 1 more, my profit goes up by $4. That sounds like a good deal, okay? So again, we're going to use this in business applications to tell us how fast something's changing, okay? Now, I don't want to have to do this for every point on the graph I'm interested in. It would kind of be nice if I had a general way to figure out the slope of a tangent line at a given point, okay? Otherwise, I have to do this. All right, let's now find it at 3, 9. Let's do it again at negative 2, 4. I don't want to do that. That's going to take me forever, right? So I want a general way to do it, okay? So that's what they're showing you here, okay, on the top of this next page. They say, don't pick points one at a time, like 2, 4. Let's look at a general point. Okay, here's where you're going to have to get out your algebra hats, okay? Now, instead of saying that the point X that we're interested in is 2.01 or 1.99, let's just say it's 2 plus some little h, okay? What's h? H is a really small number on either side of 2, okay? So it can be a negative 0.01, it can be a positive 0.01, it's small, okay? And the trick is it can be a really, really small number. How small? 0.000001, as small as you want, okay? So let's think of h as this tiny little difference between x equals 2 and x equals something else, okay? If h is small, then x equals 2 plus h is close to 2, okay? And here's the part that's algebraic. This is meant to be an ordered pair, okay? Here's your x value, 2 plus a little bit, and here's your f of x value. You take 2 plus a little bit and you plug it into f. What does that give you? That gives you 2 plus h squared, right? Because the rule for f was take the x value and square it for this particular f, okay? So this value here, this ordered pair, is going to be very, very close to 2, 4, okay? And again, the slope of the line through these 2 points is a really, really good approximation of the slope of a tangent line through 2, 4. Why? Because you can make that h part be as small as you want, okay? And you can get them really, really close. Okay, so here's a graphic showing you, here's the y value, right? Okay, here's the x value, okay, and you can see, again, I've still got a C count line, but then I can shrink down this h, okay? This point slides down here, and even this gets super small, all right? So at least graphically, hopefully it makes sense. Graphically make sense. Okay, does it graphically make sense? Okay. And then, because again, the next thing I'm going to do is talk about algebra. And from my experience, this is where most folks get lost. Okay. So at least if the picture makes sense, you're on good ground. Okay. So let's take a look. If I wanted to find the slope between these 2 points, okay, and I know this distance is the distance between my point, here's my point 2, 4. So this is the point 2 plus h squared, okay? So the difference here is 2 plus h squared minus 4. That's my change in y values, okay? And what about x? Well, this one x value is 2, and this is 2 plus h. So if I say 2 plus h minus 2, I get the h, right? So these are meant to be the differences. Okay, so think of this expression like y2 minus y1. This is like x2 minus x1. Okay, everybody see that? See what the expressions. See what the expressions mean. Anybody having trouble understanding that? Need more explanation? Okay. So again, I'm sure you've all seen the slope triangles before back in introductory algebra. Okay. So that's all I'm building here is a slope triangle. Okay. Now I'm going to put them into the slope formula down here. Okay. Here's my change in y, which is this vertical distance here that goes on top. Here's my change in x, which is the horizontal distance here. Here it is simplified to be h, right? 2 plus h minus 2 just leaves the h. Now here's the part where most students struggle. You have to remember how to square a binomial, okay? So if I take 2 plus h squared, right? 2 plus h, square the whole thing, okay? That means 2 plus h times 2 plus h. I'm putting it in the chat, okay? And what does that give you? That gives you 4 plus 2h plus 2h. Okay, so plus 2h plus 2h. And then the last thing would be the h squared. Okay. So that's where this comes from. Okay, 4 plus 2h plus 2h plus h squared gives me 4 plus 4h plus h squared. Okay. In order to do this definition of a derivative using the slope formula, folks, you're going to have to be able to square binomials. Okay. So again, just use FOIL if you must. Okay, to square binomials. Okay. Now here's this expression, 2 plus h squared. This minus 4 is still there. Okay. So let's take a look at what cancels out. See, the negative 4 and the 4 cancel out, leaving 4h plus h squared, okay, over h. What you can do then is, since there's an h in every single term in this expression, factor an h out of the top. That means divide it out. 4h divided by h leaves the 4. H squared divided by h leaves h. These h's cancel, and you're left with 4 plus h. Okay, now remember what we said about that. This is the slope of a tangent line, okay? Actually, it's the slope of a secant line between the 2 points 2, 4, and a point really close. But if we get closer and closer with those 2 points, h, the distance between the 2 points on the x-axis, gets smaller and smaller. Imagine this point sliding down the curve towards 2, 4, okay? And this slope approaches the tangent, the slope of the tangent line, right at 2, 4. What's happening to h? H is approaching 0, okay? As the points get closer, h. Okay, does everybody see that h gets smaller and smaller and smaller as the 2 points get closer together? Well, if h becomes negligibly small within the idea of a limit, I can ignore it, okay? And then my slope just becomes 4, okay? The instantaneous rate of change right at 2, 4, okay? But I need the concept of a limit with h approaching 0 in order to make that happen, okay? You normally can't just throw away variables unless you're doing some sort of a math operation. Okay? So let me pause at this point and say, does this explanation make sense? Okay, ask some questions. You can ask them in the chat. You can unmute yourself and ask. Okay, remember if it's cloudy now. It's probably not going to get clearer unless you ask some questions. Okay. So here's finally, this is what I was waiting to spring on you, the limit statement here. Okay. So the slope of a tangent line is the limit of the slope of the secant line. Okay. So basically, limit as what? As h gets negligibly small, as h approaches 0. Okay. So again, that's how the secant line approximates the tangent line. You let the difference on the x-axis between your 2 points get negligibly small. You let h approach 0, and that's how you get a limit. Okay. All right. So again, remember we asked about instantaneous velocity at a particular value of x. In other words, right at that x value, that time value, how fast is the thing moving? Okay, that's the same problem. Okay, because instantaneous rate of change is the same thing as slope of the tangent line, okay, which is the same thing as this thing we're calling the derivative. Okay, so it's important to realize the three things are the same. Okay, and I'll put them in the chat. Okay, so slope of a tangent line at a certain point, A, F of A. Okay, instantaneous rate of change, and the derivative. Okay, they all mean the same thing. Okay, so maybe if you are taking notes, you kind of want to write that down somewhere. Okay, they all mean the same thing. Okay. There's another terminology from business called a marginal. Okay, and basically what it means, okay, I'll type it in over here. Okay, how much does x change if x? Okay, so here's a definition we can use, okay? How much does f of x change if x increases 1 unit? For example, if I've got a cost function, okay, where x is the number of units I'm making and f of x is cost, okay, I want to know, if I make one more of these things, what's going to happen to my cost? Is it going to go up? Is it going to go down? That's your marginal cost, okay? Think about it. It's also the instantaneous rate of change of f of x. Okay, so marginal is another word for instantaneous rate of change, slope of a tangent line, derivative. Okay, so marginal equals derivative. Okay, again, I want to make sure you're okay with the terminology going forward. Okay, and you can use it to solve application problems. All right, let's take a look. All right, so here's some, usually these yellow boxes in your text are important things. They kind of want you to remember. Okay, so let's take a look. Okay, so here they're defining it. The derivative of a function at a point x, f of x, okay? I use a as if to pick a particular value of x, okay? Is an instantaneous rate of change at that ordered pair. The derivative is the slope of a tangent line at that point, and it's the slope of a curve at that point. Okay, so that's another way of saying it. Okay, slope of a tangent line, derivative slope of a curve. Okay, you can even put marginal in here if you want to. A function is differentiable. That means you can take a derivative, okay, if you can take the limit there. That's why we did so many examples about, does the limit exist? Okay, because you don't want to be in a situation of having to take a limit while h approaches 0 if the limit's not going to exist there. okay? So basically, its derivative exists if the limit exists. If a tangent line has a slope that's not undefined, okay? So basically, if the limit doesn't exist, where you wind up with a vertical tangent, remember those have an undefined slope, okay? Then you can't take a derivative there. Okay? So basically, this is kind of going through all the warnings about when can you do this. So let's look at some notation, okay? F prime of x, that's the way you would read it. See this little, it looks like an apostrophe. Okay, it's not, it's more like an accent mark. Okay, so F prime of x, okay, or y prime, if you're not using function notation, is a derivative. Okay, here's another way to render derivative. Okay, and they do it in a kind of hokey way. You'd say dy dx, okay, or df dx. This notation is called differential or Leibniz notation. I'm not going to use it that much, but you might see it in your homework or you might see it in your reading. So it's worth it to be comfortable with it. Why two different notations? Historical reasons. Different people working on calculus at the same time. By the way, calculus is about 400 years old. Okay, it's one of the newer branches of math. Okay, but maybe not as new as statistics. Okay, but the reason why there's two different notations is people develop different ways of talking about it, and the two different ways of notation have survived. Okay, I will use the F prime notation almost exclusively. The dy dx notation turns out to be useful in particular types of examples, and I'll point those out to you when we go along. Okay. Now you might look at it and say, what's, dy? You could think of dy dx, this being delta y and delta x. Again, it's a slope, right, folks? Okay, so a derivative is kind of a limit of a slope formula. It's really not anything super unusual. Okay, so let me stop at this point and ask, are you okay with the notation? Okay, and if you would, please just throw a yes or a no in the chat. Are you okay with the notation? Comfortable with what we're talking about? Okay. So basically, here they even go insofar as to tell you verb forms. Okay, like when you're talking about doing this operation, what's it called? It's called find the derivative of a function, take the derivative of a function, differentiate a function. Okay, so pretty much they adopt it like that, an adaptation. Notice what they've done here. Think of it like the f of x or the y has fallen off and now it's over here. So d dx is essentially the same thing as df dx. Okay, you'll see this notation in apps a lot. Okay, this d dx means take a derivative. Okay, it's kind of what lets the app go. Okay, it knows what to do. Now here's a formal algebraic definition. Remember, we've been plugging in particular points like the 0.24 and finding the instantaneous rate of change at that point. I don't want to do that for every point on the graph. I want to find a general derivative function, okay, that then I can plug in points on my original graph and get the instantaneous rate of change there. Okay, so this is a more general definition. You'll notice there's no value for x plugged in here. Okay, it says take f of x plus h and then subtract f of x, right? There's no 2 here. Okay, so this is going to give me the function f prime of x. Okay, so what's important to keep in your mind here is what we did with our graph initially was we plugged in a particular x value 2, okay, and a particular f of x value 4, and we worked out f prime of x, and it gave us a number, which was the slope of the tangent line at 2, 4. What I'm showing you here is a way to generate a function in x, okay, that's a general derivative function of f of x, right? And I can find the instantaneous rate of change anywhere on f of x with this derivative function by just plugging in the x value I care about, okay? And so again, we're going to compute exact values of derivatives with formulas, but we're not quite there yet, okay? We're still going to be doing some approximation. But this formal algebraic definition, I'll show you what we can do with it, okay? So here's the idea of a derivative as a function, okay? So we've played so far with approximating it at any x value, okay? So you can figure out, as I move around my curve, the derivative value changes, okay? So maybe I can use those values to build a function of its own, a derivative function. The input values are going to be the same as the x values on your given function. The y values are just the slope of the tangent line, okay? Now, I can say this from now till the cows come home. I have an app that's going to show you this, okay? So I'm going to come back to this, okay? But I want to go back to the app that I shared in my browser, okay? So I'm going to minimize the notes here, and then I'm going to go back to derivative plotter, okay? Can everybody see the derivative plotter? And this is the thing you have a link to. See the derivative plotter? All right, good. All right. It comes preloaded with some demo examples, okay? And this is one of them, okay? What's cool about this is it's got a slider. And as I drag the slider from left to right, what you're going to see on the graph is two things. You're going to see a tangent line travel up the curve, okay, and go around. And that tangent line is going to have a slope, okay? So let me ask you, for this part of the red graph, okay, what should the slope of the tangent line be? What kind of number? Okay, what should the slope of the tangent line be? Just right here. In other words, is it increasing? Is it positive? What's happening to it? It's a positive slope, right? Because this slopes from the left bottom to the top right. Okay, but think about it. Is it steeper here or is it steeper here? Where is it most steep? Left or right? Okay, so I'm asking you, where is it steeper? Left or okay, Jasmine's saying steeper over here on the left. Okay, and then what happens as it gets up here near the mountaintop? What about right at the mountaintop? What's the tangent line look like at the mountaintop? Okay, so I'm asking you slope. Yeah, horizontal, Charlie, that's right. And what's the slope of a horizontal line? 0, okay? So think about what you just told me. You said here, I got a positive number and it's big. Then it gets to be a smaller positive number until when I get right here, the slope of the tangent line is 0. Now imagine for all of these x values between the left end of the grid and that mountaintop, you were to plot x and y where the y's are the slope, okay? You would have a very large positive y, okay, over here. You get a smaller positive y until finally, right over here, underneath that mountaintop, you should be at y equals 0. Yes? Okay, so imagine plotting those slopes as y values. Okay, so big positive y value, smaller positive y value, smaller and smaller until right here under the mountaintop, we're at y equals 0. Okay? You're plotting the derivative function. Okay? I want to talk about it before we do it. Okay? How about on this part of the curve? Okay, the part from the mountaintop down to the valley. What do the slopes look like there? Decreasing, okay? So the slopes here are negative, okay? And they start out as small negative numbers and they get a little bit steeper. And then somewhere around they turn around and right over here, okay, you wind up with 0 again, right? Because horizontal tangent. Okay, so again, I have 0, 0, and then you can see positive slopes again all the way on out. Okay, so I want you to visualize what the graph of the derivative will look like. Visualize what the graph of the derivative will look like. I said positive y value, smaller, 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 0, negative, negative, turn around, come back, 0, positive, positive, positive. What kind of a shape did I just trace? What does it look like? An S, okay? I think I'm trying to trace something that looks more like a parabola. Parabola. Okay, right? Okay, let me actually use the applet, okay? You've been very patient, so let me show you. I'm going to drag this across. Here comes the blue tangent line, and up on the top, you'll see the green derivative, okay? And it's approximating the slope. Notice it's going down. M approx is now 3.7, 3.1, 2.93. See it getting smaller as I get near the mountaintop? And then hopefully I can stop this right when I'm horizontal. See, it's 0 right there. And look where the green line is, right at y equals 0. Okay, I'm going to keep going. Now my slope is negative, so the green line is going below the x-axis. That's where y is negative. Again, thanks. Okay, and you can see what's happening. It's getting a bigger negative number, and now it's turning around here. It's getting smaller. Right here, there's a point where it goes from bigger to smaller. Okay? And then right here at the valley, you can see I'm getting smaller negative numbers. And right here, I should wind up with 0. It's really hard to hit the mark, but you get the general idea. Okay? And then I have a positive slope all the way. Starts out a small positive number and gets steeper and steeper and steeper as I go up. And again, that's me not knowing what I'm doing. Okay, just pay attention to the green lines. See the green line? The green line is the derivative. Okay, so green line is the derivative function f prime x. Okay, of the red line. Now, some of you might, they didn't actually show you what function rule they used here. So what kind of function do you think is the red graph? What kind of function is the red graph? If you had to guess. Cubic, okay? Looks like cubic, okay? And I kind of already gave it away. Green function is quadratic. Okay, So notice there's a difference of 1 level of degree there. I start out with a cubic, okay, in polynomial land. If I differentiate it, I get something that's 1 degree less. Okay, let's try one more example. Okay, and this time I'm going to use a custom function, and this is also to show you how this works. Okay, you click over here, user-defined function, it clears the screen. Down here, don't type y equals, just type what you're interested in. How about x squared? And then hit graph. All right, there's now my red function's quadratic. Okay, and let me drag. Okay, if you take a look, okay, I'm going to drag my slider across. And you can see I start out with a negative slope, negative slope, negative slope, 0 slope, positive slope, positive slope, positive slope. So look what happens. Okay, right at that vertex, there's my horizontal tangent, positive slope, positive slope. And again, I'm drawing on the graph. Okay, so now your derivative function looks like what kind? Derivative function's the green one. Okay, what do you think that green? Linear, okay? And again, a linear function is 1 degree less than quadratic. Okay, so you've already learned something about derivatives of polynomials, okay? They drop a degree, okay, if you're talking about the function. But what I'm trying to show you here is, obviously, your starting function was a function, the red thing, and your derivative function is a function, the green thing, okay? So I wanted to make sure you realize it's more than just a value. This function has values all along the length of it, okay? And you can see them here down at the bottom as I slide along the function, down where I scribbled in blue. Okay, so I really like this app, okay? And let me just ask any questions about the app. Okay, you have a link to it, and I would strongly, strongly urge you to play with it. Okay, so you're comfortable about just what information this derivative is giving you. Awesome. Okay, let me bring up this and see where we are. So what you can do, okay, what they do in the text anyway, is they have you fill out a table of values. Okay, here's one they've done for you already, where you're sort of approximating the slope of a tangent line. Okay, and you can see in this graph over here, red slope is positive. This looks like about 1. Okay, this is a 0. This looks like about a -1. Another 0. Big number, maybe 2, maybe that's 1. Okay, smaller than 1. Okay, you get the general idea about approximating slope. You're just guessing. Okay, they didn't give you a rule. There's no way for you to figure it out. You're just guessing. Okay, so here's what they came up with. Right? They're saying at this point where x is 0, what's y? It's 0. What's the slope of the tangent line there? It looks like it's about 1. Okay, here's the next point on the graph, 1, 1. Okay, that slope of the tangent line looks like it's 0. Okay, here's the next point, 2, 0. The slope of the tangent line looks like it's a -1. Okay, then here at 3, -1. Okay, they said the slope of the tangent line is horizontal again. Notice every time the graph turns around and you have a mountaintop or a valley, your tangent line slope is 0. That's going to be very important later on. Okay, it's going to help you find these high and low spots, okay? Which in a model might correspond to a minimum cost or a maximum profit, might be useful to know. Okay? All right, so everybody understand again the idea of the table. And then they graph the x values here, these same x's with these y values. And that's how they get this graph right. Okay. So I would like to stop going through the notes at this point and actually do some examples with you. Okay, we have probably about a half an hour left of class, and I'd like to make that a little more interactive. Okay, so let me close this. I'm going to share my iPad with you, and we'll go through a few examples they have in your text. And then I have some more ones that involve some of the algebraic manipulation that we can do together. Okay, so let me just share my iPad. And hopefully, okay, so hopefully you can see what I'm seeing on my iPad. It says 2.3 exercises. Okay, everybody okay with seeing that? Everybody see 2.3 exercises? Okay, good. All right, so here's a graph they're giving us, supposedly an f of x graph. And they want us to, first of all, fill in the y values that go with this, okay? So here you can see when x is 0, y is 1, okay? And again, I'm estimating the slope of the tangent line right there, okay? I'm going to say it's 1. I'm not going to stress about this. I'm going to just take a guess, right? I'm also going to put some lines here so I don't mess up my data, okay? Okay, now if I look at halfway, here's where x is 0.5. Okay, I'm estimating what my y values are there. And that looks like it's about halfway up. Again, I'm not sweating it. Let's say it's 1.5. And the slope definitely looks like it's still positive, but smaller, not as steep as the slope is at 0. Okay, so how about if we say 0.5? Okay, everybody kind of see what I'm doing here? I'm doing what the app did, but I'm doing it manually. Okay, it's a good exercise to make sure you understand the concept of what the derivative's telling you. Okay, now let's take a look at 1 at the point x equals 1. Okay, my y value looks like it might be a little higher than 1.5. How about 1.7? And guess what? Right there, my tangent line has a slope of 0 because it's horizontal. Again, moving forward at 1.5, here's 1.5. Okay, I'm guesstimating what my y value is. Let's say it's 1.5 again. Okay, and again, look at my slope now. Okay, my slope's coming down the curve on the other side. So now the slope has a negative value. Okay, and I'm going to say it's negative 0.5. Again, not stressing, I'm estimating. Once I get to the point 2 over here, it looks like I'm right at the y value 1. And the slope has gotten steeper in the negative direction. So let me say that that slope is negative 1. Okay, everybody good with that so far? At 2.5, okay, you can see I've got a very, very steep slope. My y value is 0, but my slope has gotten really, really steep. I don't know, let me say that that's 2, or negative 2, right? Because it's still going down, okay? By the time I get to 3, my y value is at negative 1. And you can see my slope is not quite as steep as it was at 2.5, but it's still negative. Okay, so let me say, looks like negative 1. Okay, and again, by the time I'm at 3.5, my slope has flattened out again. Okay, I'm going to guesstimate what the y value is down there. Let's say it's at negative 1.5. but the slope is very definitely 0. Okay? And by the time I'm at 4, my y value is at -1, and my slope is now positive again. But again, not terribly steep. Let's say it's 0.5. Okay? Anybody questions on how I came up with the table or the graph? Any questions on the table I built? Okay. All right, now here's the fun part. I'm going to go back and I'm going to get rid of the tangent lines I drew because they're kind of in the way. And now I'm going to plot the x values that I have here, these x values, with these y values. Okay, so ordered pairs basically. And I'll try to plot them in a different color to make it a little bit more visible. Okay, so the first one is 0, 1. Okay, then I have 0.5, 0.5. Hey, everybody see where I'm getting the values from? Then I have 1, 0. Okay, and then I have 1.5, -0.5. Okay, then I have 2 and -1. 2.5, -2. Again, that's kind of hard to draw, but it should be down here. And then I have 3, -1. 3.5, 0. And 4 and 0.5. Okay, and again, if you were to sort of draw a line between, you would have the graph of the derivative. Okay, so I've taken the slopes of the tangent lines and I've graphed them as y values. How do we figure out the slope again? Okay, so again, what you're looking at is slopes of tangent lines. So you have to remember a couple of things about slopes, okay? So if I draw a tangent line to this curve, like here, okay, this is a positive slope, okay? Okay, this is a bigger positive slope, okay? This is a smaller positive slope, right? Then you've got negative slopes. Okay, and this is a more negative slope. Okay, get the general idea of how I'm getting out the slopes. I'm estimating them, but you have to kind of remember some basic things about slopes. The steeper the slope gets, either in a positive or negative direction, the bigger the number becomes, okay? Slopes that rise from the left to the right, like these ones right here, okay? Those are positive. Slopes that fall from the left to the right, like these two down here, those are negative, okay? Does that answer your question? Make sense? Okay, other questions? Anybody other questions? Okay, I'm gonna assume, since nobody's saying anything in the chat, you're all okay with this, all right? This is just an estimating exercise. Again, you've got an app that kind of does it for you if you can figure out how to graph this, okay? You can get the app to do it for you. I'm going to skip the next two since they're pretty similar, and I'm going to try to move on. Okay, so let's take a look at this one. Let's just look at some of these questions, okay? If you look at number 4, it's asking at what values of x does the graph of G have a horizontal tangent? So let me see if you can answer for A. Okay, answer for A in the chat. Okay. At what values of X does the graph of G have a horizontal tangent? Okay, and there's the graph of G right there on the right. Okay, so what X values do you think you've got a horizontal tangent? That means a tangent with a 0 value. Anybody have any ideas? Even if you can pick out one, that's great. Okay. All right, so typically you're going to give X values. You're right, Jasmine. Definitely X equals 2. Okay, so I'll say X equals 2. Anybody think of any other contenders? Okay, so here's what Jasmine's seeing right here. Horizontal tangent. How about down here? How about over here? They're not as definite valleys, okay, as that mountaintop, but I would be willing to say 1 and 3 as well. Okay. So again, what you're looking for is you're looking for turnaround points, and you can see the graph goes from decreasing to increasing right here. So that means at 1, you've got a turnaround point. It's obvious, this mountaintop's a real obvious one. You go from increasing to decreasing as you go over the mountaintop. And over here, you're decreasing down here, and then you start increasing a little slowly, but you still turn around here. Okay, so you're looking for turnaround points. Okay, so at what values of X is the value of G the largest? And where's your biggest value of the function output? Anybody want to hazard a guess at what X values is there? We're not asking you about the derivative, we're asking you about the function value. Okay. Anybody, any ideas? Okay, Charlie thinks it's the biggest here. Okay, it looks like it actually even goes slightly over the line at 6. Okay, so you could say X equals 2, 6, and maybe 2. Okay, and how about the smallest? Where's the lowest value of the function? Lowest y. If I'm looking at lowest value, this over here at 1, I can actually see part of the grid underneath it. So I'd say at X equals 1. Okay, I'd say this point at 3 is a little bit higher. Okay. Again, you will be able to figure this out once you have a little more calculus under your belt. Okay. All right, now here's an interesting, let's take a look at number 5 rather, okay? These are called like what's the story graphs, okay? And some of you are familiar with these, like make up a story that goes with the graph. Here's ones where they give you the story and you have to find the graph, okay? Now these are time velocity graphs. What that means is your horizontal axis in all of these is time, and your vertical axis is velocity. Okay, so you're talking about speed. Okay. Now, let me ask a question, okay, in the chat. What is the rate of change in English? What's the rate of change of velocity or speed with respect to time? Okay, what do we call that in English? Okay. Imagine you're riding along, it could be in a bicycle, it could be in a car, a plane, and all of a sudden your speed, your velocity changes. It either gets bigger or it gets smaller. Yeah, it's called acceleration. Okay, So what you want to figure out here is, okay, these are not position graphs. That's what you want to understand, okay? So let's take a look at graph C. Graph C is telling us as time increases, velocity stays the same, okay? So this is an object that's moving at constant velocity, okay? There is no acceleration. There's no rate of change here, okay? So anybody have any idea what that might correspond to? Anybody have any idea which one would be graph C? Who's most likely to be walking or moving at a constant speed? An unprepared student walking across campus to take a calculus test? Well, you know what? If that were me and I were unprepared, I would probably stop. I might even turn around and walk back to my dorm a little. Then I might turn around and say, oh, I might as well get it over with. I don't think I'd be moving at a constant speed. Okay. How about, again, it's kind of subject to interpretation, but let's go with this one. Okay, a student confidently striding across campus. So she or he is moving at a constant speed. Okay, so again, I'm not going to go through all these examples. I'll leave them for you to play with. But I would say that E would probably be the best match for that one. Okay, so I would match this one with. Again, it's kind of difficult because I would have done numbers for one and letters for another. It's confusing the way they wrote this. Okay. All right. So everybody comfortable with this so far? Okay. I will work through the rest of these problems and put them up there for you to see. But with the time we have left, what I would like to do is I would like to move on to show you how to use the definition of the derivative, okay, to actually calculate the derivative, okay? Because this is kind of an algebraic stretch for some students. I want to make sure you see how to do it, okay? So let's take a look, right? Now, I'm going to show you the functions, and then I'll give you one to do, okay? And then maybe I can, do some more of these. Either if we run out of time, I'll do them for you to show you. But let's just look at this first function, okay? Y equals 2x plus 5. Here's the definition of the derivative. I'll try to write it right here, okay, so you can see it. Okay, so I have the limit as h approaches 0, f of x plus h. Okay, so that's the definition that I'm using. Where did I get that from? From the yellow box in your text. Okay, now in order to use this, I need this stuff. Okay, so I'm going to start writing f of x is another word for y, so that's negative 2x plus 5, right? I'm just copying that over. Okay, f of x and y are the same thing. Now I have to evaluate f of x plus h. And what I'm showing you is do it in a separate work area. Don't try to do it while it's in the definition. It's too confusing. Okay, so what does this say? It says, take your expression on the right-hand side over here, all right, and just plug in your x plus h in place of x. So I'm going to do that. Here's negative 2. And then wherever I have an x, I'm putting an x plus h. Okay, everybody all right with that? And then again, you can simplify it a little if you want. This just involves a different distribution. So negative 2x minus 2h plus 5. Everybody all right with it? Then all you've got to do is plug it in to this expression. Okay, another thing students tend to do with this definition is they lose the limit statement out front. Okay, try not to lose the limit statement, otherwise you won't know what it is you're supposed to do next. Okay, so I'm going to put this first part up here in place of f of x plus h. Right, so that's going to be minus 2x minus 2h plus 5. Okay, this minus sign is the minus sign in the formula. Okay, everybody comfortable with that? Now, if you look at f of x, that's over here, you can see there are multiple terms in it. So when I plug that in after a minus sign, I need parentheses. Okay, why do I need parentheses? I want to make sure the minus sign in the formula will distribute to everything that comes after it. All right, so I'm just putting in minus 2x plus 5. Okay, everybody comfortable where those bits are coming from? Okay, okay so far? The denominator is super easy. It's just h. Okay. Now I got to do some algebra on the numerator. Namely, I got to distribute that negative sign. So I'm copying my limit statement over again. Right. And I got negative 2x minus 2h plus 5 minus the negative 2x is plus 2x minus a positive 5 is minus 5. Okay, so this is just algebra. Okay, everybody all right still? And now I can get rid of like terms, right? I got a negative 5 here and a positive 5 there. I got a negative 2x and a positive 2x. So all I'm left with is negative 2h over h. Okay, everybody all right with the algebra? Yes? Okay. Now what can I cancel out here? Yeah, cancel out the h. Okay. And it doesn't even matter if you let h go to 0 because there's no h in the expression anymore. Okay, you've got the limit of a constant, and that's just negative 2. Okay, so note here, okay, what am I saying? I'm saying that the derivative, or y prime, okay, here is just the constant negative 2. And if you look at what you started with a linear function. Its rate of change is always the same, namely the slope. Okay, so this isn't all that interesting with a linear function. Okay, let me try it with a quadratic function. Okay, let me try it over here. Okay, I'm going to copy this onto a separate sheet. Okay, so you're comfortable with what I'm doing. Okay, so I'm just going to move over here and create a new sheet. All right, so here's what I want to do. I want f of x equals negative 3x squared plus 4. And I want to find f prime of x. Okay, now we're using the definition of a derivative here. Okay, so we're going to have a much faster way of doing this. Don't worry. There are derivative formulas and rules that are real easy to keep track of. So you don't have to mess with this. But we're trying to figure out, this is a slope, right? So here's my derivative formula. So let me start with f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x. Okay, and again, just so you guys understand, I'm using the same x values, right? X plus h minus x. Okay, and this just gives me h. Yeah, everybody all right with that? I want you to understand it's a slope formula, just with a limit statement outside. Okay? So x plus h minus x just leaves the h in the denominator. Okay? Now, in order to do this, I need to evaluate. I've already got f plus x, f of x, so I need f of x plus h. So everywhere I see my x, I'm going to put x plus h. Okay? So the first thing I need to do here is square the binomial. Okay? And again, you can do it with FOIL, or you can remember a pattern that says square the first term, square the last term, multiply the two terms in the middle together. It's x times positive h, that's positive xh, and then double it. Okay, that's a quick way to square a binomial. And then all I have to do is plug these values in to my derivative formula. Okay, so if I highlight these, you can see here's my f of x. That's going to go here. And then I have my f of x plus h. It's here. Right? So everybody comfortable with where all this is going? Okay, so then I have my limit as h approaches 0, and then plug in -3. Okay, you can do the algebra outside, which might be easier. Like do the algebra down here before you plug it in. So -3x squared plus a -6xh minus 3h squared plus 4. What did I do? I just distributed the -3, all the terms in parentheses, right? And now I'm going to put that in here. -3x squared minus 6xh minus 3h squared plus 4. Okay, there's my f of x plus h. The minus sign's in the formula, and I have multiple terms, okay, that are coming after that, the blue stuff. So I'm putting them in parentheses, -3x squared plus 4. Everybody all right with that? Okay, everybody seeing where stuff's coming from? All right, so let's do some more algebra. Let's distribute that negative sign in front of f of x. So -3x squared minus 6xh minus 3h squared plus 4. Minus a negative is plus 3x squared, minus a positive is a negative. Okay, and then you can see what cancels out. Well, -4, +4. Plus 3x squared minus 3x squared. Okay, so what am I left with? I'm left with the limit as h approaches 0 of -6xh minus 3h squared over h. Okay, everybody all right with that? Okay. Now, if you notice, I can factor an h out of everything. So let's factor out h. Okay. I still have my limit statement. So on the top, I'm going to be left with -6x minus 3h. And on the bottom, I have an h. You can see they cancel. Okay, everybody good with that? Now I'm finally left with the limit, and I can make the limit work, hopefully, -6x minus 3h. Okay, so if I let h go to 0, does anything happen to -6x? Nope, nothing happens. How about the other term? How about minus 3h? Yeah, this just goes to 0. Okay, so essentially, if you take the limit, this equals negative 6x. Okay, and think about it. What did you want? You said f prime of x equals 6. Okay, so you started with this quadratic f of x, and f prime is a linear function. Okay. Anybody questions at this point? Questions? Again, you need to be able to walk through this process. Okay, start out by understanding the steps and then try generating one of them yourself. Okay, you're going to stop sharing. Come back to the meeting. So basically, what I'll do is I'll not only upload the video, okay, but I'll also upload what we covered here in class. But let me ask, any questions on anything? Any questions on anything at all? Okay. A bunch of no's. I'm going to stop recording.